Hello, everyone. Welcome to another Kent seminar. Today, we have Dr. Luiz Nascimento from Petrobras. He's going to give us a lecture about the implementation of a mechanistic empirical design in Brazil. So I'll give a short bio of him, and then we'll go ahead and get started. Dr. Luiz Nascimento has been working for Petrobras, a state-owned Brazilian multinational corporation in the petroleum industry, since 2003. He is a technical consultant at Product Development and Petroleum Evaluation Department of Petrobras. The Petrobras Research, Development and Innovation Center is one of the biggest applied research complexes in the world. Dr. Nascimento got his bachelor's degree in civil engineering from the Federal University of Rio Grande do Sul in 1999, with a concentration in geotechnical engineering. He also got his master's degree from the Federal University of Rio de Janeiro in 2008. In 2015, he obtained his PhD degree from North Carolina State University under the supervision of Professor Richard Kim. Dr. Nascimento's research interests are asphalt binder production, asphalt mixture and asphalt pavement performance prediction, and development of sustainable materials. It's our pleasure to welcome Dr. Nascimento here, so let's give him a warm welcome. We cannot hear you.
Oh, sorry about that. So, good afternoon. Thank you for this kind introduction, Renan, and also I'm very thankful for the invitation. For me, it's a great pleasure to be here presenting a part of this research work done in Brazil. Actually, it's not only my work, this is a teamwork, because in order to develop this framework that I'll be presenting here, Petrobras has made many partnerships with many different institutions. So here I am trying to bring to you a little bit of this national-wide work made in Brazil, okay? So can you hear me?
Yes, we can hear you, perfect. We just need you to share your screen and then we can get started.
Okay, I'm going to share my screen now. Oh, I think I shared the wrong screen. I'm not sure about that.
Yeah.
Yeah, you share here.
This one, yeah.
Yeah?
Yeah. Perfect.
Is right now?
Yes, we can see it.
It looks that I'm sharing the wrong one. Wait a minute, please. Yeah, let's go. So, the title of my presentation is Performance Engineer, Asphalt Mix Design and Sustainability, the Brazilian Experience. So my goal here is try to show quickly how a field-validated experimental and computational framework can be used to predict and improve asphalt mixture and pavement performance in Brazil towards sustainable pavement. So in the first part of my presentation, I'll be showing to you a little bit of a work on developing a framework to predict the materials performance in the field. We have a huge data set, so I'll be presenting the framework, the experimental side, the computational side, some calibration factors. And the second part of my presentation, I'll be applying this prediction performance framework in the performance engineering mix design to improve materials performance and then improve sustainability, okay? So first of all, I need to talk about the Brazilian Asphalt Research Network. It's a national-wide project in Brazil. This project is funded by my company, by Petrobras, and its funds come from the profits for big oil field productions. So down in Brazil, we have a federal law that mentions that all the big field productions should use a little part of the profit to fund the research in our national universities. So this is the research that we have been using for developing some projects down in Brazil regarding asphalt area. In this network, we have the main goal to improve an asphalt research and development infrastructure in Brazil by investing in labs, human resource development, disseminating asphalt knowledge all over the country. And regarding the technologies, the main goal of this national project is to support the mechanistic empirical pavement design guide developing in Brazil. Also developing materials performance models and two main efforts to build and to evaluate the long-term performance of asphalt pavement test sessions all over the country. This is a very important site. So actually the Asphalt Research Network main purpose is to build and to monitor performance of test sessions all over the country, so can use this field data set to validate models, performance predictions, frameworks, and so on. Here is a big picture of our national partners. We used to have 27 national partners all over the country. And nowadays we have around 10 partners working with us in network. This is a view of our field data set. By 2024, we have 65 validated text sessions. When I talk about validated text sessions, these are those sessions that we have all the data, very nice performance performance measurements, materials for testing, and so we can run all the analysis required for field validation. These are validated. In this development, we lost around 20 to 30% of our test session because sometimes we miss some data, we have some field problems, so we miss the information there. So special property of these test sessions is that we have a wide range of asphaltic materials and pavement structures. They are built in different regions, climate conditions, and traffic levels. And here we have the key points of the project. We, at the beginning, on 2005, 2004, we developed a manual, a special guide for make some to help the people all over the country to have a kind of standard to build and monitor the test sessions. Here we have some material characterization protocols, pavement analysis protocols. So this is a way to promote a kind of standardization process, and later we can compare the data from different institutions. Online database is very important. And here, another key point of our project is the pavement structure analysis tools. So we work in different level of tools, more state of practice zones based on the elasticity and very common models, and also more advanced ones based on viscoelasticity, continuous damage models, viscoplasticity, and other aspects. And also, of course, lab testing. Basically, we need to test the materials in the lab, build test sessions, observe the performance, run structural analysis, and then calibrate all the models we used to have. So this is the a big picture of this project here. And wait a minute. Here is another important project in Brazil, is the Fundão project. This project was a partnership between Petrobras and Federal University of Rio de Janeiro, and is very similar to the national project. But instead of using national test sessions, we use test sessions very close to our facilities, in the Fundão Island. Fundão Island is a neighborhood of the Federal University of Rio de Janeiro. It's a kind of on-campus, and we have many different landfills to compose these islands. So what we did here was to use the campus pavement to make a huge experiment. So there we built around 50 kilometers of testing. We have many different test sessions. We have different paving structures and materials availability. So it's a kind of a small national project. Here is a kind of cradle of the project, okay, a localized one. So in this project, we could build 27 hot mix asphalt test sessions. It's a very nice one. Even though we have only one climate and one traffic condition, we could test different materials. So it was very nice to understand, to learn from the materials. Then first we learn from the materials in this local experimental, and after we could expand to the national ones. And this is how we do, okay? So the asphalt pavement performance prediction experimental computational framework is composed by the FlexPave program. It's a program developed by the North Carolina State University. It's based on viscosity, continued damage protocols, some viscoplastic models. And here what we have is a Brazilian version where some models were integrated to the framework, especially for the unbonded materials in Brazil, because in Brazil we have different unbonded materials, different behaviors, so we need to have specific models to predict their behavior. So that's why you have a Brazilian version of the FlexPave 2.0. So we have our own testing protocols. They are very similar to the US ones, and all the performance predict for this framework is validated and calibrated by using the Brazilian pavement field session dataset functions. So demand stress already predicted by our framework are asphalt layer fatigue cracking, asphalt layer rutting, and IRI. These are already done. We have transfer function, we have reliability level analysis. And today, we are ongoing a research with the Federal University of Rio de Janeiro and Federal University of Rio Grande do Sul to calibrate structural layers permanent deformation models. In this case, we have a very special condition because in order to calibrate the models for permanent deformation of the structural layers, we need to evaluate each layer contribution to the permanent deformation individually. So that's why we have been using a heavy vehicle simulator to validate the models, and then later you'll be calibrate the models by using our national test session. It's a two-step protocol. Here's the asphalt mutual experimental framework. So it's well-known testing, even though we have some specific procedures for Brazilian materials. I think you are used to this kind of testing. So for fatigue, we use the SVCD model. For linear viscoelastic characterization, the dynamic models, and for rutting, the stress sweep rutting coupled to the shift model for prediction the rutting. So this is our experimental framework. And here the computational, it's a very common, so we have the FlexPave program. We can introduce the climate data, traffic data, material properties. So the program outliners are damage contours, pavement response, plastic strengths, and this is the where our data get in on the field validation calibration. So in order to predict cracked area, IRI, and rutting, we need to use transfer functions to validate and have some reliable models. So here is the two-step work for asphalt mixture fatigue cracking model validation. So in the first step, we analyze the Fundão project test sessions. So have a kind of local transfer function for fatigue cracking. we use different programs, but here I'll be focused on the FlexPave one. And in the second step, after we validate the models in the local, by the local transfer solution, we expand the calibration to our national test sessions. So we could validate it and calibrate and have some prediction error functions. This is a very important point here. This is, it looks simple, but it was very important for us because in order to validate the system at the beginning, we need to see if the analysis routes were reasonable. So in this case, we have a bottom layer, bottom asphalt layer, top asphalt layer. The bottom layer has a very nice fatigue performance, and the top one is in terms of fatigue is really poor. So when you run the analysis, okay, the system showed us the upper layer totally damaged. So the question is what is happening? This is happening in the field. So when there, extract the cores, analyze, okay, we have the upper layer totally damaged and the bottom layer is new, no damage in the top layer, in the bottom layer. So this kind of analysis were made for many different test sessions to identify where the damage were and if they were really damaged. And this was the first point, was a kind of validation. And then the next step, okay, we are confident that our framework, what is the framework? Lab testing, pavement analysis, computation analysis, and the results, we got confident that they make very nice predictions here. And then we calibrated these functions. This is our first function calibrate for the fatigue cracking. We capture the damage underneath the load area. And from this area, we have a grid of points, damage points, and develop a transfer function to predict the cracked area in the pavement. So these are the national test sessions. We have a very nice calibration, very nice predictions. Sometimes you have some outline, some points that they look to be outliers, but actually, when you look in this space here, we're not taking into account the timing for this damage, time or number of repetitions. And for fatigue cracking, once the pavement start to crack, the cracks grow really fast. So we need to take a look on this data. Even though we have good data here, it's important to take a look in this data by considering the time. So this we have some validation test sessions. They are not included in calibration. And here we have the number of load repetitions, different test sessions, and for the same damage level, cracked area level, it's we compare the predicted load repetition versus observed load repetition, and you can see that you have a very nice predictions. This is even though we have some outlier here regarding observed versus cracked, when you consider the time or the number of repetitions, they are very close. For pavement design, this is very important. For performance prediction, this is very important. Then here we have some examples of different test sessions all over the country. We have totally different materials, climates, traffic levels. The red lines are the predictions. The blue lines are the observed performance regarding cracked area. And here we have in bio-asphalt test sessions here. We have some experiments on this regard. You look at this test session, it is not cracked. I remember this is a test session from São Paulo University, and the professor told me, "Hey, Luis, we had a problem here. The test session is not cracked. It's not cracked. So how can we calibrate and validate the models if it's not cracked?" No. It was nice. It was perfect because we have too many test sessions, too many different damage levels. If it's not cracked, the model should show us that it's not cracked. this was exactly what happened. So we got really confident about this, and especially because it was a very different condition here. In São Paulo, we have some special soils with lateritic behavior. So the engineers from this region, they can combine aggregates with this soil to produce really good unbound materials, stabilized materials. And since they produce a very nice pavement structure by using these materials, the pavements present very nice performance. And whenever we consider these properties in the analysis, we got very nice performance here. So that's good. That's good. This is another example. It's a very different material here. It's a synthetic binder. Let's make time here. Okay. This is a synthetic binder, and it's not an asphalt material. We use the same experimental protocol, the same framework, and you see here the as-built property allow us to make this prediction in blue, and the field observed one agrees with the predict one. So even having a different material, we could make a very nice prediction. This is the same framework for the routing prediction. So in the first moment, we took a look on the validation sessions, then we made some national calibration and very nice ones. So one point I would like to mention here is that when comparing our calibration of the routing model with the US one presented by the North Carolina State University, we have about the same calibration. So if we have low standard prediction error, this is good because it's like you can use the same data for calibration, validation in US and Brazil. And also, I will not be presenting the IRI prediction validation because it follows the same procedure, and we got about the very nice prediction capability too for this model. So at the end, what we have here is a framework that is ready for reliability-based pavement analysis. So we have experimental, well-defined computational framework, well-defined variables. So whenever we put this variable here, we can predict pavement stresses with a certain reliability level. This looks simple, but it's very important, very important. Behind this graph, we have too many informations, too many work, and it's a time-consuming work here. So doing this, predicting something with certain prediction error requires a huge field data set, and we already have performance this. So what are the applications for this framework? The field validate framework for asphalt mixture and pavement performance prediction can be used for different purposes: mechanical, empirical, pavement design, development of asphalt binders, classification systems, new binders. We can take a look in the crude oil composition, asphalt binder performance, paved performance, can link this. But for today's presentation, I brought some example to balance mix design you can use for the performance engineer mix design, and how can we use this performance engineer mix design towards sustainability in the pavement, in the pavement area. And here we have our performance engineer mix design framework. We have what we do here. We have the pavement performance. So we use some performance volumetric relationships. So we can predict from VFA, VMA, the cracked area, the routing performance by using our framework. And then we can make some assumptions, optimizations, and we can have the cost models and some sustainability models. This is a big picture. It's very important. A key in this process is the performance volumetric relationship. And this is the way we do is based on the North Carolina State University protocol. We have a kind of a volumetric space here. So we define some points for characterization. We call these 4 corners. And with these points, we predict the performance, and we calibrate the performance by using VMA FA. Once you have this performance calibration, we can optimize it and find the best point here for optimize the material's durability. This is an example here. So we have pavement conditionals, the four corners, the volumetric space, and we have functions for rutting, for fatigue. So we can optimize it according to the practical requirements. This is an example here. It's how can we integrate the mixed design to pavement performance. So we have a kind of typical pavement here, some project requirements. We have a 10 centimeter asphalt layers, a traffic level, the design, and the maximum allowed rutting of 7 millimeters and 30% of crack area. So looking at the results of the performance engineer mixed design, you can see the super pave mixture, the typical not optimized one, with 4% avoid, didn't attend the minimum required. We have a higher rutting when compared to the limit. It's a shorter fatigue life when compared with the end design. And when you optimize it by using the balanced mix design based on the pavement performance, we see that we could improve the materials performance. Look here, we kept the same the pavement thickness. We could improve the rutting performance and also improve the fatigue performance. So it's a really powerful tool, because by optimizing the volumetric space, we could improve a lot the material performances, even on the rutting side and the fatigue side at the same time. But the problem here is that even after optimization, we couldn't achieve the minimum fatigue life required by the project. So something that we can do is, okay, we have the rutting achieving. In order to have the fatigue life attended, we can make the pavement thicker. So for the super pave mix design, in order to have to attend the project service life, we need to increase the asphalt layer thick from 100 millimeter to 150, and to the optimized mixtures, only 20 centimeter, only 20 millimeter was enough to achieve the target. So we can see that we have a very nice one. So after this optimization, you can see clearly that the BMD could promote and improve on the pavement. So another option, another choice we can have is by applying a balanced design plus when we change the material. Here we need to increase the pavement thickness. And in this case, what we do is replacing the conventional binder by a polymer modified one. So checking again, once you change the binder and we come back to the pavement analysis, we could see that by changing the binder, even having the same pavement thickness, we could achieve all the targets for the design. Even in the fatigue life, we obtain a longer fatigue life when compared to the project. So it's a way to fix this shortcoming here. So this is a big picture of how this performance engineer can help us. And when you look to the carbon footprint reduction on the map for asphalt pavement, we see that the main technologies that are mapped to help us on reducing the carbon footprint is the use of RAP. So when you walk on this roadmap through the time, you see today you have 20% of RAP being used regularly, and increasing. We have it's predict we need to increase the RAP use in the asphalt pavement. Also, we need to reduce the asphalt concrete temperature. So our mixed asphalt should be apply more and more and more. And at the future, maybe we need to have cold mixes. So basically, from today to the future, what we need to do in order to reduce the carbon footprint is biomaterials, 100% recycling, cold mixes. Yeah, of course, for the equipments, for our machineries, we need to use biofuels and electrification. This is a kind of roadmap very well known for the community, Europe, US, South America. All the research have about the same big picture about this roadmap. But one important point that we need to consider here is that as we move in this line, we need to keep the performance, because we can save some energy, some materials when we use wrap, when we use the warm mix asphalt. But it's important, we need to save in the materials and improve the performance. And also, we need to take into account the pavement service life emissions, because you have some emissions from the pavement maintenance, traffic emissions, and end-of-life impact. So everything should be considered on the sustainable pavements. And a key point on this regard is the balance mix design. In order to make all these materials have a good behavior in the field, we need to use balance mix design to guarantee that they perform as required. So this is a key point in the sustainable pavements. And the NAPA is a National Asphalt Pavement Association in US mentioned that. Here, the balance mix design is actually sustainable by itself. Whenever we make an optimization, we can improve a lot the materials performance and also can save a lot of materials. Look at this example here. We have a certain pavement condition. We run 95% of a reliable level analysis. We have some cracked area, traffic level. And what you have here, we have different performance materials. These classes here are fatigue class of the asphalt mixtures. So also from class number 1 to class number 5, you are improving the material performance. Also improve the material performance, we analyze in the flex pavement, can see that the layer can have a feeder, can be thinner, so we can save a lot of material. For a poor fatigue performance material to have the same durability, we need to have 17 centimeters. For the total improved performance material, can have only 9 centimeters to be able to have the same durability. So my point here is that from our experience in Brazil, once you have a balanced mix design, usually we can have one class jump every time. So we can come from here to here, we can come from class 2 to class 3, and we can improve a lot the material and then save a lot of materials. And when you use the balanced mix design plus, that is, when you replace some materials, especially the asphalt binder, usually you can jump 2 classes, so we can save a lot. So BMD sustainable by itself is a kind of drop-in technology. Here is an example of performance engineering BMD for rapid usage in Brazil. You know, while in US 20%, 22% the average wrap usage in the asphalt mixtures, in Brazil we are just beginning to use wrap. So for us it's a challenge to switch, because in our roads we have a lot of flexible pavements, so we have a lot of fatigue problems, and we have a very heavy traffic here. But this example is a very nice one that I brought to you. This is a 50mm asphalt overlay, and the typical solution in this highway is a 19mm nominal maximum aggregate size here with asphalt rubber. So in this highway, people usually do a 50mm highway with asphalt rubber and 100% of mid material. So our challenge here is using a performance engineer mix design to replace this layer by using about the same gradation, but with 20% of reclaiming asphalt pavement and a 58 minus 22 unmodified binder. It's a kind of binder designed for rejuvenating the wrap. So the question is, will this new mixture be able to support this traffic? So we have a very heavy traffic and critical weather condition. Here we have some parameters here. The region is São Paulo. We have some traffic speed. We apply a 95% of reliability. It's a 6-year project. And here we have the pavement structure. The good news from the pavement structures is that here it looks that we don't have a kind of fatigue life dominating process here. Is the main concern here is about the rutting, because look, we are using a asphalt rubber, that is materials that has a very nice rutting performance in Brazil, and we are replaced by a 58 minus 22. So in order to apply this material into this road, we run our performance engineer mix design. We have some road concession pavement design limits. For the rut, the maximum is 7 millimeters, cracking the maximum is 15%, the IRI is 2.7. We have a very high level of IRI allowed in our roads down in Brazil. So this is the result of the test. So when we run the performance engineer mix design, we only had these red lines. They are the as designed ones. So for cracking, for IRI, for what we did these predictions. Here is the actual pavement design life expected for the road concessions. So in all the simulations, after the optimization, we could see that all the limits were attended by our project. So we apply the material in the field. The material is there about 2.5 years, and the blue points are the observed one. So this is very nice one results, because regarding IRI, you are in the model, the fatigue cracking too. In the last field inspection, we could see some small cracks start to appear. So it makes sense, because our model is saying that it's time to appear the cracks. And for rutting, that it was the big concern of the people from the for the agency. We did this prediction, and the blue points are following our prediction. So very nice results here, and the material is there. And nowadays we are expanding this technology to other highways of the concession. We are doing new tests there. This is my last slide. Deixa eu ver, like this is my time. I'm going to finish. So so far we talk only about performance engineer mix design. That's the focus of my presentation. But also it's very important to consider the environmental product declaration in this process, because we cannot mitigate what we don't measure. For example, in this case, in our examples, we have different solutions, but the asphalt mixtures can present different performance and also different greenhouse gas impacts. So it's very important to use it to couple this environmental product declaration to the performance engineer mix design. So here we have some third-party validator LSA analysis, and I brought to you some example here that you need to think about. These are some carbon footprint of some hot mix asphalt and warm mix asphalt. They came from the same asphalt plant. Here we have a hot mix asphalt with conventional binder, is a PG 70-16 here, and here we have a polymer modifying binder with PG 76-22. So we can see that in both cases, the ore mix asphalt technology could reduce a lot the footprint, the carbon footprint of the asphalt mix. So one point that I would like to call your attention that when you compare the ore mix asphalt with a typical binder with the mix asphalt with modified binder, seems to have a huge difference in the temperature of production. We got a very different impact of this mixture. So here is around 40% higher when compared to the ore mix one. So when you do all the balance, we need to think about the thickness reduction, the durability was enough to give us a more sustainable pavement. This is something that we need to think about. So the points I would like to point out here are ore mix asphalt technologies are more than welcome on this journey to reduce the carbon footprint. And the next generation of balanced mix design should consider the asphalt mix APD as a kind to combine performance with the environmental impact in the same analysis. This is something important to do. So my final considerations here is the Brazilian field validate framework for asphalt mixture and pavement performance reduce is reliable and can be used for a wide range of materials and applications. So we have a huge field data set that has proven that. So the balanced mix design and the performance engineering mix design, they are a key point on improving asphalt pavement performance and sustainability. There is no choice that this approach, this framework is a key point for the pavement sustainability. And our changes now is performance and prediction tools require a wide field validation, so it's not easy to do. It requires time, it requires resources, it requires people, equipment, so it takes time. And the presented performance engineering mix design framework is time consuming. It is a big issue here. Usually we spend 10 full days of live working to run one set of performance engineering mix design. So this is my presentation. Sorry for my English language. My English is a little bit rusty, and thank you so much for your attention.
Thank you, Dr. Nascimento, for this nice presentation. We have people here in ICT. Also, we have people on Zoom. If someone wants to ask any question, feel free to do it. We have some questions here at the classroom.
Yeah.
Thanks a lot for your presentation. It was really interesting. So I was just wondering, when you showed the field validation of the pavement model, are you doing any sort of calibration for each and every sections?
Sorry, I didn't understand this question. The sound is not as good as. Could you repeat your question, please?
Can you hear me now, Professor?
Yes.
Doctor, sorry. So I was just wondering if you did some sort of calibration for the models to match the prediction for the field measurements, or is there any sort of calibration done here?
I'm sorry, Henna, could you help me on translation? I'm not understanding his question.
Okay, I'm gonna translate it to Portuguese. Eu acho que ele tá falando do slide sobre a validação em campo exatamente essa. Is this one, right? The next one? Yes. No.
Yeah. So did you do calibration for each and every different section?
Ele está perguntando se tem alguma calibração específica para cada test section.
No. Actually, this is a very nice question. Thank you for. We have more than 50 national test sessions and around 24 test sessions in our Fundam project. So the transfer function is only one for all test sessions, only one transfer function. So once you run the analysis, we use the climate data for test of test sessions, the material properties, the traffic pattern. So we run the simulation. Once you get the computation analysis, we use the transfer function to predict the cracked area. But the transfer function is the same for all the experiments. It's only one transfer function.
Do you need to follow up?
I have a follow-up. So
I think he can hear.
okay. So also you mentioned like you predicted IRI and compared IRI. So how did you measure IRI in the field?
The cracked area?
The IRI, how was IRI measured?
How our eyes was measured by using the laser integrator. We have some. It's a very common way to measure. We have some lasers, so you can measure the pavement longitudinal profile, and then this profile we put in the golden car algorithm, and so you have the IRI. So all this procedure is very standardized procedure. We use the same ESTM standard as used in US. So for IRI predictions, what are we observing our test sessions? Since we don't have asphalt rutting bigger than 6, 7, 8 millimeters, the asphalt rutting was not sensible. The IRI was not sensible to the rutting of the layers. So the only variable that you capture from the analysis is the damage simulated by the flex pave, the initial IRI. From these two parameters, we can predict the IRI along the time. So this is the point.
Yeah, thanks a lot.
Professor Raj is raising his hand. I think you can unmute yourself and ask the question.
Yeah,
Hi,
thank
Professor.
you. Hi, Luis. Thank you for a great presentation. Really nice work, and good to see the Brazilian approach that you guys are using. My question is about the modulus input for the FlexPave model. Usually with these kind of damage models, especially if you're looking at bottom-up fatigue, the modulus is very critical for, that's the critical thing basically, because the strain can be much lower if you have a high modulus. Did you conduct any sensitivity analysis looking at the modulus? And I ask this because, for example, if you start to include a lot of RAP, I know you mentioned RAP is new, usually the modulus will get much higher, and actually you'll have a very good bottom-up fatigue cracking by these type of models. So did you conduct any sensitivity analysis for the RAP?
Very nice questions. In our pavement data set, even though we have a lot of test sessions all over the country, we didn't have RAP mixtures applying the field. So our transfer function actually is not calibrated theoretically, it's not calibrated for RAP mixtures. But since we are capturing the asphalt mixture RAP dynamic modulus and then the relaxation modulus, and we capture all the fatigue properties by using the SVCD analysis, when you combine the asphalt mixture properties in the FlexPave framework, so you have different pavement responses according to the climate, to the traffic level, to the pavement structure, and these responses, when you couple to the SVCD model to that mixtures, so the prediction looks to be fine, because now we have been applying some RAP mixtures in Brazil using the same calibration, and it looks that the RAP mixtures are following the same pattern of the other ones. So it looks that the mechanistic approach is able to capture that. At least so far, we're having this observation. Moreover, I use one example with the synthetic binder, and synthetic binder, they have a different rheology, different temperature sensibility, and even though having this different behavior, we could predict nicely the materials performance. So of course, we need to investigate more the RAP usage in this protocol, but the initial results using different materials, biomaterials, synthetic materials, and RAP, they are telling us that our actual transfer function can handle this kind of materials too. But we need to check better. It's a very nice question. Thank you, Professor.
Great, thank you. And we are also working with the bio. So I talked with Camila a lot about this material, and it's very different. Actually, the rheology is very different, and it's interesting. So thanks again. Great talk.
Yeah, the rheology is very different, and also the aging process is different, and maybe in the transfer function can have some flaws when trying to apply. So it's a very nice point.
Okay. Angeli has another question here in the classroom. So maybe I can hand the microphone to you.
Thank you for the nice work and the nice presentation. I just have a question in relation to the cracked area comparison, the prediction observed. This one that you're showing right now, these are all the sections that you tested? Because I'm trying to understand. So clearly here, right, there's some data that are far from the unity line or equality, but so I'm curious, like what is the point that is plotted on the one that's number of repetitions per cracked area?
Let me see if I understood your question. Here we have the observed cracked area. So we walked on the pavement and we measure the cracked area. And in the x-axis, we have the predicted from our framework. So we apply the transfer function and we compare observed versus predicted. So in this data set here, what we have, some test sessions, we have 1 or 2 cracking observations. Another one, we have 3. When we're comparing here, the cracked area for all the test sessions we have in our network. You see, all predictions versus all observed one. So maybe for certain test sessions we have 2 points, to other one we have 1 point, to other 3 points. So this is our data set here.
Just a small follow-up on the plot that you had where you have number of repetitions as your X. So you were tracking over time how was the cracked area evolution over that number of repetitions to failure? Is that right?
Sorry, I didn't understand the question. You mean how do we measure the cracked area, or how frequently we measure the cracked area?
When you had plots of the sections, I think ID 14, I don't know if this one. Oh yeah, this one. I was just curious. So you were measuring at this number of repetition at a different time point. You will measure the cracked area and then compare with the simulation. Is what was done?
Yes, yeah.
Okay, I see. Thank you.
You're welcome.
Okay, so I think it's time for us to wrap up here. Thank you, Dr. Nascimento, for the presentation again. Really appreciate your time with us. Oh, okay. Okay, yeah, it's 2:50. I need to wrap it up. Okay. So thank you very much, and thank you everyone for joining us.
Oh, you're welcome. For me, it was a great pleasure to be here sharing with you a little bit of our work made in Brazil. And thank you so much for the kind invitation.
Thank you. Thank you.